Okay, here's our more general case. Okay, first we still have M data points. Okay? Now, M is going to be the dimension of the space you map onto, just like it was when we did the previous model. And our image space over there, or our codomain, whatever it is, was R3, so we could visualize a plane and a normal vector, right? We don't want to restrict ourselves to that, okay? That would restrict us to 3 data points, because you've got more than 3 data points, you need more than a 3-dimensional space. But the thought process is identical. We just can't see it, okay? So we could have any number of data points, and we could fit this to any degree polynomial where n is less than m. If n was equal to m, you'd be able to solve it exactly. You'd be able to fit the polynomial to the points. You'd set up the simultaneous equations. You'd get a square matrix. And unless you have redundancies in your x-coordinates, everything's going to reduce. And you're going to get a solution. You're going to get your C1, Cn through C to C naught. Everything's going to be fine. You're going to be happy. You're going to have a great model, but it's probably not going to mean anything. Because a higher degree polynomial fit to, an n degree polynomial fit to n points, just wiggles around and goes through all the points and doesn't really tell you much. Okay? Okay, so n is going to be less than m. If n is greater than m, you in general won't be able to solve it. If you got a degree 6 polynomial and only 5 data points, you're not going to be able to fit them. Okay? Now, if you have more data points than the degree of your polynomial, as was the case when we had 3 data points trying to fit a linear, 2-parameter degree 1. And you know what? There ought to be n minus 1. Okay, anyhow, we'll worry about that later. Okay, where n is less than m anyway. Yeah. So this is the case when m is greater than n, where we've got to come as close as possible, which is what we just looked at. And what's it look like? It looks just like it did, except we can't be specific about planes and normal vectors, okay? So here we've got Rn. Now our transformation now there are n of these, right? Okay? I was about to write y1 through ym, but that's not going to work, right? So I'm just going to say, well, that's Cn minus 1, x1 to the n minus 1 plus down to C1. And then it's Cn minus 1 times xm to the n minus 1 and all the way down to C0, just to give you a picture of what that is. Okay? Our goal is this should be as close as possible to y1 through ym. Okay, so we have our A. We know what our A matrix is. Well, in this case, A equals being careful. X1 to the n minus 1, x1 to the n minus 2, down to x1, so that we get this, right? Because we multiply this row by this column, this is what we get, right? And then it just extends down to the other rows, xm to the n minus 1. Then down to xm, and then a 1 at the end, because we've got to multiply something by c naught, right? And it's got to be 1, because we're going to get c naught. Okay? And that would be like x1 to the n minus 1 down through x1 to the 0. Another way to look at it. Okay? So we have our A matrix. What else could we possibly need? Just the ability to reason through the process and a picture to help us, to help guide us. Okay? So we have Rn here, and this matrix obviously maps Rn to Rm. Okay? Because there are m of these. Now, analogous to what we had before, draw it like kind of a rectangle. It kind of represents a plane, but it's a higher dimensional version of a plane, but notationally it's just more numbers. Okay? So you have your column space of A. Okay, and these are just numbers, so you write down your column space, do some row reduction, all that stuff, and see what the dimension of the thing is. Do all the stuff we've learned to do with matrices. So here's our column space, and this is, of course, the row space of A transpose. And that's our image space. It's the row space of A transpose because the row space of A transpose is the column space of A. That's what the image has to be. And down here, we've got the null space of A transpose. Why is that important? Because Rm is a direct sum of these two spaces. Any vector in Rm, and that includes this one, is one of these plus one of these, right? And that's the key. So here's our y1 through ym. And I hope I'm not over. Yeah, I'm not even close to 15 minutes. I hate to split videos. It takes a long time. Interrupts my workflow. Prone to errors. Okay, we have this. Okay? That's our target, but we're not going to be able to hit it because anything we transform is in here. Okay? So, here's our transformation. I'll use A, just identifying the name of the matrix with the name of the transformation. Okay? Being a little sloppy about that, but I'm going to be. I mean, this class for engineers, you got to be a little sloppy. I'm just digging at engineers. I love engineers. Okay. Then engineers get to dig right back, so feel free anytime. Okay, so here's where we are. Okay? And we want to find, basically then, we just want to find the two vectors here that add up to this one. The vector in here will be the projection of this vector. Your original question, I never did answer it. So here in a minute I will. Why do you subtract the projection? Well, actually I kind of did, didn't I? Yeah, I did. Okay. So anyhow, the vector you get in here is the projection of this vector into the null space. What's left over is what's in your image space. Okay? So that's kind of worth noting. So we have then two vectors here. Okay? Now let's be consistent with my notation. I think in the notation, the problem I asked you to work on, that's W, right? So what you have here is the projection onto the null space of W. Okay? Now, it's not a projection just onto a vector, it's a projection onto a whole blame null space. It's going to be some linear combination of the basis vectors for your null space, which you can easily get from your transpose matrix. Okay, by something you learned to do a couple of months ago. Okay? So there's your projection. And what's this vector? This is the vector you want, so you can take it back here and find out what it came from, which gives you your C naught through Cn minus 1. Okay? And this vector, I'm just looking for a place to label it, is W minus its projection. Okay? This is the vector that's as close as possible to this one within this space. So that's a big deal. I'll say closest possible image vector to W. By image vector, I mean image of a vector over here. Don't have room to write out all those words, but we understand that. So now all we got to do is take this thing back here. This is what we want. That's this, that's our plot. So let's just put some notation on it and we're done.